Welcome to Season 2 of the Carroll-Wells Gradient. In this episode, we move from interpretation to testability. This is Episode 13, Layer 13, Experimental Predictions, where we ask a simple but essential question. If persistence, information, and thermodynamic constraint really do shape structure at every scale, then what should we actually see? Not dramatic effects, not violations of known physics, but subtle fingerprints. Small biases that accumulate over time. This layer is not about proving a framework correct. It is about making clear how it could fail. Up to now, we've treated persistence as a quiet influence. It does not drive evolution directly. It does not override randomness or force outcomes. Instead, it acts as a weak bias, shaping which structures last long enough to matter. If that picture is accurate, then its effects should not appear as sharp signals. They should appear as statistical tendencies, patterns that emerge only when we look across large data sets, long timescales, or vast regions of space. That expectation guides every prediction in this layer. The first class of fingerprints involves directional variations. Standard cosmology assumes large-scale statistical symmetry. On average, the universe should look the same in every direction once local effects are accounted for. Persistence-based effects do not violate that assumption outright, but they allow for the possibility of tiny residual asymmetries, leftover structure that was not perfectly erased. These would not appear as obvious alignments or preferred directions. They would show up as weak correlations in polarization, lensing patterns, or background radiation, signals that survive averaging just barely. If future data continues to tighten constraints and these effects vanish, the hypothesis shrinks. If they persist, they become places to look more carefully. The second class involves what can be called persistence drift. If persistence acts as a long-term bias, then distributions should not evolve exactly as purely memoryless models predict. Instead, small deviations should accumulate. Structures may appear slightly more stable, slightly more correlated, or slightly more resistant to dispersion than expected. This does not mean dramatic departures from standard models. It means small mismatches, the kind that only become visible when precision improves. Persistence drift would be subtle, statistical, and cumulative. A third signature appears in void ledger behavior. Cosmic voids are often treated as empty regions, but from a persistence perspective, they are records. They preserve information about what was displaced, reorganized, or failed to persist. Voids are not blank. They are structured absences. If persistence leaves a ledger, then void properties, their shapes, alignments, and correlations may encode more history than simple density models predict. Again, the expectation is not dramatic anomalies, but coherent patterns across many voids. Voids remember what structure forgot. A fourth class of hints involves pulse and entropy relationships. If the universe's expansion and structure formation carry long-term persistence effects, then entropy production may not be perfectly uniform across cosmic history. Certain epochs may show slight deviations in how efficiently structure exports entropy. These are not oscillations you could see by eye. They are faint signatures in background radiation, structure growth rates, or gravitational wave backgrounds, patterns that only emerge through careful comparison. They are hints, not declarations. What unifies all of these predictions is restraint. None of them require new particles. None of them require modified gravity. None of them violate general relativity, quantum field theory, or thermodynamics. They live entirely within existing observational programs. That is intentional. This layer also makes something else clear. Failure is informative. If directional variations disappear with better data, that constrains the framework. If void statistics align perfectly with memoryless models, that narrows the space further. If entropy histories show no residual structure, the idea collapses cleanly. There is no rescue clause here. Persistence either leaves faint fingerprints or it does not. Layer 13 is not about certainty, it is about honesty. A framework that cannot be tested is not physics. A framework that survives only by adding complexity is not science. What matters is whether subtle, cumulative effects appear where theory says they might. If they do, the framework earns attention. If they don't, it dissolves quietly. Either outcome is useful. I'm Charles Carroll. Thank you for listening to episode 13. In the next layer 14, observational synthesis, the universal persistence map, we will step back and look at how all of these observations fit together, not as isolated signals, but as a single map of structure, history, and memory written across the universe.